about some inequalities. Let's try this again. First one had technical difficulties. It was almost done. Got cut off. It was a terrible tragedy. But enough about me. Let's solve this polynomial inequality. So here's how we're going to do it. We're going to, just like a polynomial equation, we're going to get 0 on one side and factor. And I'll explain why with a graph in a second. But let's just factor this first. So we're going to get x minus 6 times x plus 5 is greater than or equal to 0. Then we're going to take a number line and plot those points with an open circle because we have a greater than sign. If it's greater than or less than, it's an open circle. Greater than or equal to or less than or equal to, it's a closed circle because we want to show that those zeros, see these numbers will make the left side equal to 0, which is not greater than 0, so we want to show that these points are not solutions, but points just to the right and left of them will be solutions. So now we have a number line with 3 intervals on it. X is less than 5, x is less than negative 5, x is less than 6 but also greater than negative 5, and x is greater than 6. So if one number on that interval is a solution, then every number on that interval is a solution. And that has to do with the graphs of polynomials being continuous. And we'll look at that once we find our solution set. I'll explain why. You could just test one point. So let's start off from the left. Let's test a point like x is negative 6, because that's a number less than negative 5. So right now we're testing a point on this interval. If x is equal to negative 6, we have negative 12 times negative 1 is positive 12. And that is greater than or equal to 0. So that means every number on this interval is a solution. Now let's try 0. 0 is in between negative 5 and 6. When we plug in 0, we get negative 6 times 5 is negative 30. That is not greater than 0. So we're not going to highlight anything on that middle line segment. Now let's test x is equal to 7. That's an example of a point on the rightmost interval. That gives us 1 times 12, which is 12. And that is greater than 0. And that's a solution. So every x value greater than 6 is a solution. So our final answer is if x is less than negative 5 or greater than 6, it's a solution to this polynomial inequality. Now, just to further understand what we did, let's look at the graph. So here we have it on Desmos. In blue is x squared minus x minus 30. And you'll see it crosses the x-axis at our two what we call critical numbers. So when we factor a polynomial, the zeros are called critical numbers. And that's where the graph will change from positive to negative and then negative to positive. So if you look at all x values less than negative 5, we have outputs that are positive. And then right at negative 5 it equals 0. And then when it's greater than negative 5, x, all these y values are now negative. Now because these graphs are continuous, it's never going to cross from negative to positive without hitting 0 first. So that's why we could just test one point like 7, and if we get it makes the right side equal to 12, then we know all these x values will make the right side greater than or equal to 0. So let's try another one where it's a factor by grouping. So let's see. Okay, drawing mode. So actually before we do that, let's just recap what we did. So to solve an inequality, we're going to get 0 on one side, find all the zeros, those are called our critical numbers, and we're going to put them on a number line from least to greatest. And then we just test one point in between each critical number. Like we saw with the graph, polynomials are continuous. So when you plug in a certain x value, you get a negative, every number on that interval will be negative, since it can't become positive without crossing 0 first. If you get positive, every number on that interval is positive. And then if you can, check your work with a graphing calculator. So with this polynomial inequality, we're going to factor, because it's a polynomial, and that's how we solve polynomial equations, so that's how we find the zeros. So we're going to put it in standard form first. So I'm going to subtract 6 on both ends. And you get 0 over here. And on the left side, we get 2x cubed minus 13x minus 8x plus 52. Sorry, 52. Because it's 58 minus 6. We're going to factor by grouping by pulling out an x squared. And we get 2x minus 13. And then in the last two terms, pull out a negative 4. And we get 2x minus 13. Factor further, and you get x squared minus 4 times 2x minus 13. And we could take that difference of two squares and factor it down. And we get x minus 2 times x plus 2 times 2x minus 13 is greater than or equal to 0. So now on our number line, we can plot 3 points with closed circles now. 6.5, because that's 13 over 2. We can plot positive 2 and negative 2. So now we have 4 intervals to check. So here's a little trick if you have it greater than or less than or greater than or equal to or less than or equal to 0 on one side. When you plug in a number, don't worry about what value you get for the left side. In this case, worry about whether it's going to be positive or negative. So let's say we plugged in negative 3. Well, then negative 3 minus 2 would be negative, and then times negative 3 plus 2 would be negative, and then times negative 3 times 2 would be negative 12 minus positive 13 would be negative, and then we'd get a negative times a negative, which is a positive, times a negative, which would be a negative. So that means if you plug in negative 3, it's going to make this entire left side negative, which means this interval right here is not part of our solution set. All x values less than negative 2. Alright, then plug in 0. When you plug in 0, you're going to get a negative times a positive times a negative. And that will become a positive, which means every point that you plug in between negative 2 and 2 will give you a positive number. Now let's try it with a number between 2 and 6.5. Try 3. You get a positive times a positive times a negative, because it'd be 6 minus 13, which is negative. So that would multiply out to a negative. So that's not a solution, but the last one was. So let's try one more. X equals 7 would be a good one to plug in. That would give us a positive times a positive times a positive, which is positive, which means every x value on the interval greater than 6.5 would give you a positive output. So our final answer, the solutions that would solve this inequality, would be any x coordinate less than or equal to 2 and also greater than or equal to negative 2, or an x value greater than or equal to 6.5. And we can confirm this by looking at our graph, and it'll be in red, and you'll see, alright, for x values we plug in greater than 6.5, we get positive y values. If we plug in anything between 2 and negative 2, we get positive y values. That polynomial in red is greater than or equal to 0. On the other hand, any x values less than negative 2 or in between 2 and 6.5 give us outputs that are negative. So the graph is a great way to check your solution set. Alright, let's look at some unusual cases now. So we looked at the directions earlier, and we saw that to solve polynomial inequalities, we want to get 0 on one side, and all of these inequalities have 0 on one side. And then we try to factor. But what if you can't factor? Something like x squared plus 5x plus 10 is not factorable. There is not two numbers that multiply to 10 and add to 5. So we'd have to do the quadratic formula. Now, if we did that, so if we try to find the x values that made this expression x squared plus 5x plus 10 equal to 0, if you can't factor it, you have to do the quadratic formula. So we get x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c. Now right away over 2a. right away I could tell this discriminant is going to be negative 15, which means this is going to have no real solution when we solve the quadratic equation, which means there's no x values that makes this equal to 0, but there may be x values that make it greater than 0. So in other words, this expression that I kind of covered, now you can see it, does not have any points where it hits the x-axis, which means it never crosses from positive to negative or from negative to positive, which means it's always positive or it's always negative. So to check, we could just check one point. It's like we plotted our number line and we had no critical numbers to put on it, so we just test any number on this interval, which could be any number. So let's say you plug in 0. X equals 0 works, which means every point works. So when we're talking about the polynomial inequality, the solution would be x belongs to the set of all real numbers. Any real number you plug in there will give you a y value or an output greater than 0. So that's going to happen when you can't factor it and you know there's no x-intercepts, so you just test a point and it's all or nothing. And we can confirm this by looking at the graph. If we look at x squared plus 5x plus 10, we'll see it's a parabola that is facing up and the vertex is above the x-axis. So every x value will make this expression greater than 0. So that's why we get all real numbers is the solution. Let's look at the other example on the right. So here, on the right, x squared plus 5x plus 10 is less than 0. Well, we just saw from the graph and from the quadratic formula, it never crosses the x-axis. And we saw by testing a point that it's going to be facing up. And, well, we knew that from the positive leading coefficient and from looking at the graph. But by testing a point and seeing it was positive, we could tell this graph is always above the x-axis, which means it'll never be less than 0. So this inequality has no real solution, or just no solution. Okay? For this one over here, in the bottom left-hand corner, we're going to just treat it like a normal polynomial, factor, and we get x minus 3 times x minus 3 is greater than 0. So what we're going to learn, and what we'll introduce right now, is that when you have a repeated 0, like x equals 3 works for both factors, that means your graph is going to bounce off of 0. So it's either going to like hit off 3 and go back up, or come from the bottom, hit 3 and come back down, right? If this was the x-axis, now is the y-axis. One of those things is going to happen when you have a repeated solution. So we could just treat this like normal and plot our x-intercepts on the number line. We would have 1, it would be at 3, and we'd give an open circle because it's greater than, not greater than or equal to. We could test a point like, let's say 4. If you plug 4 in here, you get 1 times 1 is 1, and that is greater than or equal to 0. If you plug in another point, like 2 or 0, you would get 9 is greater than 0, which is true. So your solution set is pretty much x can equal any number except 3. So you just say x cannot equal 3. If you want to say x belongs to a set of all real numbers, comma, x can equal 3, that's fine. But you could just write x can equal 3 here. Alright, and we can confirm it by looking at the graph. So if we look at the graph of x squared minus 6x plus 9, we see it's going to hit x equals 3 at one point, and that's the only point where the graph equals 0. Everywhere else it's greater than 0. And because we're looking for all x values that make it greater than 0, that's why we just have x can equal 3. Alright, and then let's look at one more over on the right. So let's factor that, and we'll see that's also a perfect square trinomial. That's going to be x plus 4 times x plus 4. And now we would have one point with a closed circle, x equals 4. If we plug in 5, we get like 9 times 9 is greater than or equal to 0. That's true. If we plug in 3, we get 7 times 7 is 49. That is greater than or equal to 0. So this would also be somewhere where or in a scenario where your solution set is all real numbers. Every number works because there's one x-intercept, and that's a solution because we can see when it equals 0 because of the greater than or equal to sign, and then anything on the interval on either side of it will make it also greater than or equal to 0. And if we look at the graph, we'll see x squared plus 8x plus 16 is always, the output is always greater than or equal to 0. Because it just bounces right off that point. X equals -4. Alright? And although, just quickly to talk about it, if let's say it was different, if it was negative x squared plus 8x plus 16, when is that greater than or equal to 0? Since it never crosses the x-axis, it's only on the x-axis. So if I were solving this solution set right here, when does this graph that's graphed over here, when is that polynomial greater than or equal to 0? This would be no solution because it has one x-intercept, and it would be, well actually, sorry, if it would be x is equal to -4. But if I made it strictly greater than, when is this greater than or equal to 0? Sorry, just greater than, not greater than or equal to. If it was this right here, there'd be no solution because it's never greater than 0. It's always less than or equal to 0. Sorry for that addendum, that ended up being more confusing, but just, if you always factor, plot the critical numbers on a number line, and test points, use closed circles when there's an equal sign, use open circles when it's just less than or greater than, you'll never fail. But just pay attention to these special cases. Sometimes you get weird answers, and you're not doing anything wrong. And it's especially going to happen when there's one x-intercept or no x-intercepts. That's when you get the solutions like x just can't equal one number, x is all real numbers, x is no solution, or there is no solution. Alright, let's look at rational inequalities. So, hold on, let me save this video. Alright, sorry about that weird intermission. I just wanted to save the video in case I lost it again. So let's just finish up with rational inequalities. They're very similar to polynomial inequalities because we're going to find critical numbers and test points on intervals. But how do you find the critical numbers? So you're going to get 0 on one side. You're going to get a common denominator and write the rational expressions as one big rational expression. And the zeros of the numerator and the denominator are going to be your critical numbers. So any domain restrictions, any x-intercepts, any asymptotes, any holes, they're all going to go on your number line. Anything that makes the numerator or denominator 0, once it's one rational expression and it's factored, is a critical number. And then we test points, right? So let's do that, and we'll look at the graph and see why it makes sense. So, got a little work to do here. We got to get both expressions, or all three expressions on one side, and then make it one big rational expression. So we're going to start off, we have 3x over x minus, alright, a lot of technical difficulties today. Sorry about that. So let's get everything over on one side. We're going to subtract x over x plus 4 over on the left side, so we get negative x over x plus 4. I'm leaving space for when I add my common denominator, and then subtract 3 on both sides. And on the right side, we'd have a less than or equal to 0. So now let's get a common denominator. So I'm going to multiply the top and the bottom here by x plus 4, and the top and the bottom on the other expression by x minus 1. And then here, I'm going to multiply the top and the bottom by x minus 1 times x plus 4. And that's x squared plus 3x minus 4 when you multiply it out. So then our numerator is going to be 3x squared plus 12x minus x squared plus x minus 3x squared minus 9x plus 12 all over x minus 1 times x plus 4, and that's going to be less than or equal to 0. So the numerator will cancel out, so we get, those cancel out, we get 12x minus 9x is 3x, and then plus x is 4x. So then we get negative x squared plus 4x plus 12. So that's going to factor. You factor out a negative 1, and then it's going to be x squared minus 4x minus 12. So that's going to be x minus 6 times x plus 2 over x minus 1 times x plus 4. So now we have 4 critical numbers. So we're going to take our number line, and with closed circles, we're going to plot a negative 4. We're going to plot a negative 2. We're going to plot a 1, and we're going to plot a 6. So now we have 6 intervals to check. So again, we can do like our plus or minus, our positive negative test. And what I mean by that is, so let's plug in a number less than negative 4, so like negative 5. It would make, so we'd have a negative here times a negative, so we're at positive, times a negative. Okay, so now the numerator is negative over a negative times a negative. So all of these little green checks would be negative. So it would be a positive over a negative, which would be negative, which means the graph would be less than or equal to 0 on that interval. Alright, if I plugged in, let's say, a number between negative 4 and negative 2, alright, it would make, this would be negative 1, and then negative 3 minus 6 would be negative, and then negative 3 plus 2 would be negative, so our whole numerator is negative, and then negative 3 minus 1 is negative, and then negative 3 plus 4 is positive, so that would be a negative over a negative, which is a positive, so this interval over here we're not going to shade in. Alright, and then let's try a number between negative 2 and 1, so 0. So it would make negative 1 negative, it would make this negative, this would be positive, so now our numerator is positive, and then x minus 1 would be negative, x plus 4 would be positive. So it would be a positive over a negative, which would be negative, so we would include that interval. Alright, now let's try 2. 2 would make negative 1 negative, and then if we plugged in 2, x minus 6 would be negative, this would be positive, so now our numerator is positive. If we plugged in 2 in the denominator, either factor will get positives, so we have positive over positive, so the interval from 1 to 6 is not a solution set. There's no solutions on that interval. And then last but not least, we could plug in a number greater than 6. So we would get a negative and then a positive. If we plugged in 7, positive, positive, positive. So all the factors would be positive, but this negative 1 makes the entire rational expression negative. So we're going to highlight that interval. So that's what our graph would look like. So our solution set would be x is less than negative 4, or x is less than 1 and greater than negative 2, or x is greater than 6. And all those should have equal to signs because it did originally. So that's our final solution set. Last but not least, let's look at the graph of that, and we'll see. So first, here's the graph before I got a common denominator, and then this is what we had when it was factored, and you can see it's the same exact graph, and hopefully you could tell, alright, from all x values less than negative 4 up until negative 4, and this vertical line represents the asymptote, the output's going to be negative. And then, since negative 4 is undefined, we get this weird discontinuity here. So rational expressions are not continuous, but they're only going to change from negative to positive when one of the factors change from negative to positive. So in other words, at the zeros of any of the factors of the numerator or the denominator. So the factors of the numerator are x-intercepts. Like here, we got x equals negative 2 and x equals 6. And then the factors, or the zeros of the denominator, represented by this orange and green line, those are asymptotes. And at these points is when it changes from negative to positive to negative to positive to negative. And I'm going over my arrow right now, but I don't think you could see it. But It's those two black points and the orange line and the green line, the asymptotes and the x-intercepts. So the graph just further shows that the output's going to be negative when x is less than -2, -4, sorry, in between -2 and 1, and less than 6. So I believe that is it. I hope you found this video helpful. Let me just double check. Yep, that's the last slide. Thank you for watching, and I'll see you in class.